Hello and welcome everyone. Let's solve this Leetcode challenge that is actually from Sean Prazad list and it says to move zero. So we are given an integer array of norms. Norms is our input array and we are to move all zeros in this array to the end of the array while maintaining the relative order of the non-zero elements. So basically any element that is not zero. So we can see an example in this problem that we're given. We have an array of 0, 1, 0, 3, 12, and at the end of the output what they expect is that the numbers, the non-zero numbers, are moved to the first order and the zeros are moved to the end of the array. Now there's an really interesting caveat where we must do this in place, which means that we should not create a new array, or we should not create a new storage technique. We should return that same. We're basically evaluating or solving this problem and returning this array without making a copy. So Leetcode is going to be checking or running a test on this norms array, not any other storage that we create. So to check the norms after our code execution returns the answer. Now that makes it more complicated, but let's go over to solutions. And the first one is the brute force approach. So when you see a problem like this, while learning, the first thing that we want to discuss is how might we solve this problem. We're not thinking about efficiencies. We're not thinking about what special technique is out there. How might we solve this problem? If you are given this problem right now, what would you do? Actually, what we are going to do is what we've been told not to do, but it helps to think from that approach and then move on from there. So we are going to take all these 0, 1, 0, 3, and 12. If we were not given the constraint of not being an array, what we want to do is you want to, first of all, write an algorithm. And when I mean an algorithm, it doesn't mean writing out the code, but like a pseudocode. How would you approach the problem? The first thing I would do is to traverse the entire array, which essentially means to loop through this array, and then obviously I would have an extra container somewhere. And what I want to do is I want to check for the elements that are non-zero. So if I loop through my array, I go through the first element, it's a zero. I don't want to do anything, right? I don't need that. Then I move on to the next element. Now this is not a zero, so I have one. And then we move on to the next element in the array. We see that it's a zero. I skip over it. I move on to the next element. This is 3. This is 12. Now, this is my solution. This is the brute force approach. And it helps to think about your code that way. However, this is not the solution because we are supposed to return extra zeros at the end of our array. That's what makes it complete. In which case, we are not watching for that. Now that we have solved for the brute force approach to basically just pack our non-zero elements and store them somewhere. Now, getting the zeros is pretty easy. The thing, what you want to do for brute force is either you want to keep a count. So, for instance, while we are traversing this entire array, if we encounter a non-zero element, possibly want to have a pointer somewhere, and our pointer is initially zero. So, whenever we encounter a non-zero element, we increase our pointer by 1, and if we encounter another one, we increase it by 2. And at the end, the number of counters that we have, we append that number of zeros. So if our pointer at the end of our traversing is 2, then we just append 2 zeros to it. Or you take the length of your new array and take the length of your previous array with all of the numbers, and the difference means that, the difference is the zero element, and then we can append the number of zeros to our array. Now that's a brute force thinking. How do we make our code more efficient? Now, if you encounter an array problem, there are a number of techniques that can make solving easier that you need to know, and one of them is two pointers. So two pointers basically means that you have two pointers basically. So you have two pointers on any element in your array as you solve, or perhaps you already know you can have them start at the same point, they might start at different points, they might start somewhere else. So it basically depends. But two pointer is a very good algorithm thinking to have in place when you want to solve a problem such as this. And in this case, if we are to solve a problem in place, it's best to use a two pointer. And how are we going to use a two pointer in this case? So we want to have two pointers. They both start at the first place. And then we want to move our right pointer. Our right pointer is going to be faster than our left pointer. So whenever we encounter a zero element, what do we want to do? So essentially, we want to move our right pointer. We do not need to move our left pointer. It could be right pointer. We do not need to move our left pointer because it's a zero element. We do not need zero elements. In this case, as zero elements are useless to us, we only need the non-zero elements, and zero elements are placeholders for the remaining space that we have in the array. So now we've encountered the zero element. So what do we do in this instance? We move our right pointer. Now we encounter a non-zero element. When we encounter a non-zero element, we want to swap places with our left pointer. We want to swap places because essentially we kind of know that if our left pointer has not moved, then that is a zero element placeholder. Does that make sense? So if we have our left pointer and it's not moving, we know that we only want to move our left pointer if we encounter a non-zero element. And the fact that our left pointer hasn't moved, or we are working with the assumption that wherever it is, that means it is a zero element, and you can easily swap spaces with our left and right pointer. So what we'll be doing is we'll be moving the element at our right pointer, we'll be moving it over to where our left pointer currently is. So where zero is, then we place one. We place one there. Now, it helps if you have a pen or paper to visualize these things, even as it's explained. So you move when you encounter a non-zero element, you swap places with your left pointer, and then we increment our left pointer. By default, our right pointer, we are always moving. Let's take our right pointer as the first one in the race. It's always moving regardless. But our left pointer only moves if we encounter a non-zero element. Now, when we encounter a non-zero element, our right pointer checks. Now, oh, this is a non-zero element. Then we swap spaces with what we have for our left pointer here. Now we move on. Our left pointer is now here, and our right pointer is here. So our right pointer does nothing because it's a non-zero element. So what do we go ahead to do? We go ahead, we move on to the next element, which is 3. Now 3 is a non-zero element, and what do we do? Since we've encountered a non-zero element, so the algorithm is if we encounter a non-zero element, swap spaces with the left pointer, and the left pointer only moves after after the right pointer has encountered a non-zero element. So now that 3 is a non-zero element, we know that it is time to swap spaces with our left pointer. We do not care whatever was here before, because we've moved whatever was here before to a different location. So one is essentially not lost. We still have one somewhere else. So don't think about it like, oh, what happens to one? It's been moved already. So now we swap spaces with 3. So we move 3. When we swap left and right spaces, we move 3 to where left pointer currently is. And then we move, now after we swap spaces, we move our left pointer. Right pointer is always on the move anyway. So we move our right pointer to the last element in the array. And what do we do with our right pointer? Our right pointer, we check, is this a non-zero element? Yes, it is a non-zero element. And so what do? We move it to where our left pointer currently is, which is a 12. Now, what do we do with the remaining spaces? We populate it with a 0. So the algorithm would be we have a left pointer, we have a right pointer. Whenever our right pointer is always on the move, right pointer always on the move. If our right pointer encounters a non-zero element, non-zero element takes the place of left pointer, and then left pointer moves. And so the algorithm runs till we get to the last element in our array, and then we populate the remaining empty spaces with 0. Now let's jump right into our code to see what that looks like. So let's define our pointer. So we have left pointer, which is 0, and then we want to have a loop. Basically, this is our right pointer loop that is moving regardless. So we want that to be right equals to 0, while right is less than the number of elements that we have in our array. Then we want to increment it for as long as the condition is true. Now, what do we want to do? If we encounter a non-zero element, according to our algorithm, we do nothing. But if we encounter a zero element, we do nothing. But if we encounter a non-zero element. So if our current number is not zero, what do we want to do? We want to swap places with our left pointer. So basically, the number on the left becomes the number of the right. We're swapping places. And then we also want to increment our left pointer. I want to make sure to move forward. Now, at the end of all this, we also want to make sure to append our zeros. So we do not want to forget that we have zeros. So if we run this right now, just to show you what that looks like. So if we run this right now, we can see that the norms is 1010312. The output is 1312. So we have moved our non-zero elements to the front. However, the last two elements does not populate zero. It should contain zero, but we are not populating with zero yet. So we want to go back to our code and make sure that we are populating that with zero. So basically, let's go ahead and write that code. Since So we're going to basically get the index at which we stopped seeing non-zero elements. So left I is going to go to left, and while that is less than the length of our array, because we still need it to match up with the length of our array, and we're going to increment that. So we want to populate all of those empty spaces, or basically spaces that there is no longer zero elements with zero. So when we run that, we can see that this populates the remaining index with zero. So basically, if our left index stops at this index, I think this is index 4. Now, from index 4 up to the length of the array, up to the end of the array, we want to go ahead and populate that with zero. That's basically what's happening here. Now we can go ahead, submit this, be sure that that checks out. Cool, and we can see that it's accepted. So for the time complexity, obviously, this is O of n because our code runs for as many inputs as exist in our given input array. So although there are two for loops, but this is never going to be more than the length of the given array. In fact, it could be less, it could be negligible. But yeah, that is just the case. And for space complexity, we're not using any extra memory. We did it in place. So we have constant speed. So it's fairly efficient. I hope you like this. I hope this was helpful. Please give a thumbs up and subscribe if you found this helpful in any way. And I'll see you in the next video. Bye.